Hello everyone, today let's dive into the exciting world of piezoelectric actuators, essential devices in today's technology that trigger precise movement and enable a variety of cutting-edge applications. The history of piezoelectric actuators begins with the discovery of piezoelectricity in 18th century by Pierre and Jacques Curie. Thanks to this discovery, scientists in the subsequent years have developed piezoelectric materials such as quartz, PCT, lead zirconium titanate, and polymeric materials to take advantage of this unique property. When piezoelectric materials such as quartz is subjected to an electrical potential difference, its atoms move altering their position. This causes a mechanical deformation in the material, stretching or contracting, sliding. This deformation creates a change in the shape of the material, which, depending on the configuration of the actuator, can move different mechanical parts, such as a brush or a lens. On the other hand, if the material stops receiving voltage, it will try to return to its original shape, allowing precise control on movement and position. There are two major classifications for piezoelectric actuators, by their mode of operation and by the type of material they are made of. Piezoelectric actuators, by their mode of operation, can be bending, extension and contraction, or sliding. Bending. They use specific shapes such as thin sheets or discs by applying voltage on this part and bending is generated. Both the direction and magnitude of this bending depends on the orientation of the piezoelectric crystals and the magnitude of the applied electrical voltage. This deformation can be very precise and controllable, which is why they are often used in high precision motion and positioning, such as microscopes or autofocusing systems. Physics instruments (PI) devices are based on bending. There are many for different applications. Extension and contraction. In this, the part is thought to have a linear extension or contraction and usually have shapes depending on the type of expansion required. Tubular or pillar or column shapes are used for deformation along one axis. Laminar for one-dimensional deformation, block or disc shapes for deformation in all directions. The choice of shapes depend on the application and the requirement of the motion. These elements have a great advantage, and that is their fast and precise movement, which is why they are used in applications with precise displacement, such as optical adjustment in microscopes or cameras. Noliax piezoelectric devices are of the extension and compression type and mainly alter their shapes based on the application. Their prices vary based on the specific of the application, but the most common, the NAC20XX series platens, cost around 20,000 Colombian pesos or $16. Sliding. For these specific shapes are required, such as tubes or stacks of laminates, which allow a linear movement. When voltage is applied, a controlled deformation occurs along an axis, which also generates linear sliding along that axis. They are also used in optical applications. Smart Act offers options of micropositioners based on the sliding principle, such as SLC 1720, which costs around $500 or 2 million Colombian pesos. Piezoelectric actuators, according to the type of material used, can be ceramics or polymeric. Ceramic are inorganic materials composed of metallic and non-metallic elements, which high hardness and temperature resistance, although quite brittle. The main ceramic used in these actuators is PCT, Actuators of this type have high strength, stiffness, speed, and excellent stress response. However, they are brittle and susceptible to mechanical stress. Nanopositioners are an example of an implementation of this technology, such as Morrow RLS P77, costing around 4 million Colombian pesos or $1,000. Polymers are composed of long molecular chains based on covalent bonds, are light, flexible, and electrically insulating. Given these properties, they are more flexible and lighter than ceramics, but they are slower, so they are used in softer and slower applications, such as in the medical field. Noliax NAC 20XX series piezoplatines are made from NCE46, a polymer, and are priced at around 70,000 Colombian pesos or $16. In the real world, these actuators have many interesting applications, such as ink injectors. Uses expanding ceramic piezoelectric and allows for controlled and precise ink flow in certain types of printers. Micropositioning in microscopes. These devices typically use ceramic bending piezoelectrics, which allow moving sample or focusing lenses in high precision microscopes. Ultrasonic traducers. They are used in the generation and detection of ultrasonic waves in the medical and inspection area. They use response ceramics, which are piezoelectrics that vibrate when receive an electrical voltage. Shrink cake actuators. They use piles of ceramic shrink grade materials and are used in valves and pumps for precise control of fluids. Sliding actuators. From sliding ceramics, fine adjustment of optical component and nanometer positioning can be realized. Smart windows. Piezoelectric suspension actuators made from polymers aid in adjustment of opacity in smart windows. Autofocus systems. Thanks to the fast and precise movement of the ceramic suspension, we can achieve efficient autofocus systems. Video stabilization systems. By making use of the expansion and contraction properties of ceramics, a small but precise control of video stabilization is made in the different cameras. Control medical injector. Using piezoelectric polymeric expansion, which allows a smooth and controlled dosing of drugs as in infusion pumps. In short, piezoactuators are a fundamental building block of modern technology, enable unprecedented precision and control in a variety of critical applications. We encourage you to explore this field further and keep abreast of continuing advance in piezoactuators technology. Thanks you for joining us on this journey to learn about piezoactuators.